Hello guys and welcome back to my YouTube channel. Today we will be discussing dynamic routing protocols. Alright, let's dive in. So dynamic routing protocols allow you to automatically discover and adapt to change in the topology without manual user intervention, like a actual engineer going to actually change and configure things. It does it automatically, right? So it automatically discovers and updates optimal paths between routers, allowing for real-time adjustment to network change. Let's say like a link goes down, right? Let me actually show you. Let's just wait for packet tracer to actually come up. So I'm gonna give you like a little example. I'm not gonna configure it yet, but this is just to show you what I mean by it dynamically or automatically being able to adapt to the change in the network. All right, let's just say these are all configured with OSPF and are in the up state, right? Let's say typically, let's say, it typically goes through here first, then through here, and then through here last. And then let me see if I'm able to draw an arrow. Just do black, do boom, boom. So that way, that way, and that way. Hopefully you can see that that's an arrow, right? So traffic typically goes this way, and let's say this one gets shut down. Let me actually get rid of it just to show you. Let's say that this connection no longer works, right? So it will dynamically adapt to that change and start routing traffic from that way that it typically was going to this new way, which will be this way. It will start routing traffic this way. All right, that one came out a little better. Okay, it goes this way, right? Like that, right? Instead of it going like this where it was previously. So that's how it dynamically adapts to it. It will allow, or it takes time of like convergence for it to actually start flowing traffic this way. But it will adapt to this link not being able to transmit traffic this way. All right, but let's get back to here. So it adapts to network topology changes, like I just showed you earlier, rerouting traffic to ensure connectivity during outages or congestion. And again, it significantly reduces manual configuration from engineers having to do static routing, as well as minimizes human errors. So sometimes you can fat finger a command, like for example, you put, let's say, 192.167 instead of 168. Like that could be the human errors that it can avoid completely, saving network time. Excuse me, it also saves time and network management. It is essential for large and complex, rapidly changing networks where static routing would be too rigid, and error prone. Right? And then there's these types of dynamic routing protocols. Automatically discovers and updates optimal paths. We said that earlier. It's pretty much the earlier slide. All right, again, it automatically updates. It's improved for scalability. For example, it would be easy to actually do static routing here, but let's say you have static route. Let me get it to fill actually. Jesus. All right. Um, let's just do a circle. All right. Let's say you have one here, 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 here. Right. These are all different routers, right? It would be a lot of work, manual labor, and potential errors to actually configure all of these with static routes instead of using a dynamic routing protocol, right? So that's why it's easier to actually use one instead of going into each CLI and typing in the command to the next hop or exit interface, right? It also provides fault tolerance, automatically reroutes traffic in case of network failures, as I showed you earlier. If it goes if it goes clockwise, typically, then it will, and it senses that a link going clockwise is down, it will route it counterclockwise just to ensure that it's still able to reach that host over here, right? Reduces maintenance, less needs for constant manual adjustments, reduces administrative workload and errors. Types of dynamic routing protocols. So there's link state, which allows the routers to build a full connectivity map of the entire network, sharing only link state status updates with all routers. It adapts to change on the network faster, but there is more bandwidth actually being used, right? An example is OSPF, ISIS, and it's ideal for complex networks since it can adapt to change fast at rapid speeds compared to the other one, which will be distance vector. Well, let's show you. Types of dynamic routing protocols are OSPF, link state, ISIS, again, it's a link state. RIP is a distance vector, and BGP is a path vector protocol, which we covered earlier in a different video. EIGRP is a hybrid. And then this is the identifier in the routing table. If you show IP route, or if you do, let me show you. You'll actually be able to see the table and the contents of it. Let me just fast forward a little, just to have it avoid the boot up. No, and show IP route. So it actually give you the table, so you don't really have to memorize it. You just need to know the command show IP route, and then it will give you the routes that it learns via the routing protocol, or if it's been given statically. Let me find the S here. Static, local, connected, things like that, right? So you don't really have to memorize it, but it is good to know, right? And then this is the default administrative distance, right? So connected local, static route, EIGRP summary. And administrative distance is used when there's multiple routes in the routing table, or excuse me, there is multiple routes to the same destination using different routing protocols. And the thing with administrative distance is the lower the better, right? So let's say you have one that's a connected route, OSPF, EIGRP, and static. It will use the lowest administrative distance would be the connected one right here, which has 0. So the lower the administrative distance, the better, the most trusting it is, right? And you can actually configure the administrative distance, and I'll show you that later as well, right? But administrative distance is very important when you have multiple routes to the same destination using different routing protocols, okay? Although always choose the one that's lower. Routing table with dynamic routes. You can see O is for, where is it? OSPF right here. These are learned OSPF, so is this one here. And you can see administrative distance is 110. Static is 1. And connected is directly connected. Right. But it's always good to know that OSPF is 110, okay? OSPF is a link state routing protocol for IP networks. How it works, routers exchange link state info to create a network map using Dijkstra's algorithm to find the shortest path. It organizes routers into areas for scalability and efficiency. And then these are the states. Down means that there are no hello packets received from the neighbors. And it means that it sent a hello packet, but there's no two-way communication. Two-way means it's bidirectional communication, meaning router A and router B can communicate like a ping, basically, right? It can talk, and then there's a response that will come back to it as well. XStart routers determine the DR, or designated router, and exchange sequence numbers. Exchange is when they exchange what they have, basically. They're like, oh, I have X, Y, and Z. What do you have? Oh, I have ABC, right? Basically, they exchange the information that they have in their database description, right? Or DBD. And then loading is when they actually do the exchanging. Oh, I'm missing A, send that over to me. Oh, I'm missing X, give me that one, right? And then full is when they have matching databases, so they have everything synced up, right? And then these are the packets. Hellos are used for neighbor adjacencies and maintaining them, as well as discovering. Database description, or DBD, describes the router's link state information. Request is to request a specific LSA from a neighbor. Link state ACK, or LS ACK, or link state acknowledgement, acknowledges the receipts of LSAs. LSUs are used to flood LSAs around the network. All right, that. And then these are the actual configurations as well, right? And we'll do some of that in a bit. Let's see if there's any more. All right. So OSPF areas segment networks into smaller geographical. Let me actually show you here, right? So instead of running OSPF on all of this, that will take a lot of time as well as bandwidth, and it's not very easy to troubleshoot it. So if you segment, it's like sort of like VLANs, and we'll do a video on that as well later. So let's just say this area 1 is having issues, right? Instead of going to area 0 and area 2, we can just go directly here because it's isolated, right? And we're able to troubleshoot much easier instead of having OSPF on the entire thing and then having to go into each router and see where the issue is occurring, right? Into optimized routing, backbone area, the core of OSPF, all other areas connect to area 0, the non-backbone area, numbers like 1, 2, 3, so on and so forth, connect to area 0 through organized managed routes. All right, and the benefits of an area. Divide large networks, making OSPF more manageable and efficient, and they also reduce the size of the routing table. For example, this might be, instead of having this one router have routes to here, all the devices or the routers here, it only has to these 3, and then to these 3 as well here. Well, this one has to these 3, instead of having the routing table being flooded with all of them. Instead of having 8, 11 routes, right? It only has 3 here. Improved convergence, so it's able to adapt to change much faster since it's only within a select few routers here. So instead of adapting to 11, it adapts to just these 3 right here. Local logical segmentation with areas, improved network design, and troubleshooting and control. Like I said earlier about how it isolates certain issues instead of having to go into each CLI and then try to figure out which one is having the issues or causing the issues, right? And then the router ID is a unique identifier for each router in OSPF, typically represented as an IP address. It helps identify routers in OSPF tables and distinguishes them between the different routing decisions. The assignment is typically highest manually configured IP address. If there's no manually configured, then it goes to highest loopback address. If there's no loopback address, then it goes to the highest IP address the highest IP address on a physical link that's active, like up, right? And the router ID doesn't change unless OSPF restarts, ensuring a consistent identifier during network operations. OSPF metrics and cost. A metric is used to determine the best path in OSPF based on link bandwidth. Lower cost equals preferred path. Default calculation, cost is calculated as 100 million bandwidth. A 100 Mbps link will cost 1, right? Manual adjustments, you can use the IP OSPF cost to manually set the cost on an interface and influence the routing decisions. And that's pretty much it. Let's see if we're able to. Let's see if we're able to do a little lab. Let's say. We'll do just 3 areas. Let's lower this here. And this is probably the most tedious part, just actually connecting the end devices. And let's say, get a switch here, here, and here. Let's get, I'll just put one end device in each area. So we'll do one here, here, and we'll do one here. Let's connect them as well. I have to add, let me see. I'll actually come back when the lab is set up, alright? Give me 1 second. Alright guys, I'm back. I just finished the topology. No configurations are done, but this is it. Here it's area 0. They're all going to use a process ID of 1. This is area 1, area 2, and area 3. Actually, but yeah, let's go ahead and get started. Let's actually assign this copy. We'll start configuring the PC first. Let's use the first available as the default gateway. So the second, perfect. Here we will do, so first we'll configure, we'll do the basic configurations first and then we'll do the OSPF, right? So interface, IP add, we'll do paste 1 and do subnet mask, no shut, exit interface, IP add, and then this is a /30. Basic configurations are done here. Besides the OSPF, we just added the IP routes. And then I'll actually show you that there's no route currently on it besides the local and connected. Do show IP route. Alright, that's it. Do the same thing here. Copy that. Go here. For now, we're just doing the basic configurations, ensuring that they have an IP address and that they have a default gateway and that their interfaces are active. And now we have to wait for it to power on. No, and conf T interface IP add, paste that there. 1 subnet mask, no shut, exit. Let's do the serial 0/1/0 IP add. And then just to show you, there's nothing there yet besides connected and local. Same thing here. And they're all done mainly on layer 3 devices. Like if you enable IP routing, on a layer 3 switch and no switch port, then you can have it there. And routers, of course, are layer 3 devices as well. Interface. Let's actually see which one it is. There we go. One. Oops, forgot the subnet mask. See, it removes the, well, this not specifically, but DHCP would remove the actual like fat fingering that might happen if you do manual configurations on everything. We'll actually get into DHCP at a later date, but for now we're doing OSPF, right? And then let's do the serial interface. And then do show IP route just to show you again. There's nothing there. Then let's do this one. Let's actually enable run just to make it easier for us to actually see the interfaces that we're going to be working with. And what LLDP is just a neighbor discovery protocol directly attached only. And you can see quite a bit of information. Like for example, if you go really detailed, you can see the native LAN, the duplex, the IP address, the software version that the other device is running, as well as the port that it connects to on the other device, and the local port that okay, so this is so if you do show LLDP neighbors, you'll be able to see the local port, which would be the port here, and then the port ID, which would be the port that the local port connects to on this router 5 over here. So let's do LLDP run, and then let's just interface if we're able to see actually. No shut, exit. And then do show LDP neighbors. Actually fast forward a little because it does take I think like 10 seconds for it to actually sync up. It's enabled here. So why is it not going through? Might be. Alright. It's not going through. Alright. Let's see if fast forwarding does anything. Because it should already be up. It's enabled globally on the devices. Either way, we'll try and give me 1 second. I'm gonna try and reload them to see if they're able to. Alright, so I'm back. Apparently LLDP does not work on the serial interfaces, but CDP does, and we did CDP run, and then do show CDP neighbors, and now we're able to configure them. Let's change the host names as well as these. Let's do host name. We'll have them correspond to their area. So, router 1, host name R1, R3, R2. And then let's run this command again. It should be, and it's still not populating as what it is configured as. There we go. I guess it needed time to update. Alright, so this router 1 interface should be this one. Interface, IP add. And remember, we're going to use the second available IP address since we used it. The first one on this interface here. This one is the R2. R2 is the 12 right here. And they're all point-to-point connections. Here, we'll just move this to the side a little bit. R3 is this one here. All right. Now that we have done basic configurations, we'll now do router or OSPF, the dynamic routing protocol, right? Let's get into, we'll do this one last, but we'll do these areas first, right? Let's do router, OSPF, and then they're all going to use a process ID of 1, right? Just different areas. They're multi-area route. All right, router. We can configure the router ID. We'll do it on the central one. We'll give it a router ID of 1.1.1.1, and then I'll show you how to actually make it stick. All right. Network. First, we'll advertise this network here. So 192.168.10.0, and then OSPF uses dynamic or wildcard mask. Let me actually show you. So wildcard mask, and what a wildcard mask means is that only the zeros have to match. So only the first three octets have to match, which would be this interface here, advertising this network, right? And the 255 can be any address, so from 1 to 255, or from 1 to 254, because 255 is the broadcast, right? But yeah, it's going to advertise the 192.168.10.0/24 network. And then we'll have to do area, and we'll have to specify area 1. Right? Very important that we make sure it's advertising the appropriate area, right? Now it's going to be advertising this, and enables OSPF to send or advertise this network. We're also going to have to do this point-to-point connection, the serial connection between our router 1 and then this router here as well. Let's go ahead and do that. Let me do that. Scroll down. We'll do network again. And then remember, it advertises, it uses wildcard mask, right? And an easy trick to wildcard mask is basically subtracting the number. For example, 30, it would be 252. So you subtract 250. So the main number you're going to be using is 255. So you subtract the 30, which would be 252. So that would be 3. So you'd use a wildcard mask of O.O.O.3 to advertise this subnet, right? Area, and then this is area 0 right here in the middle. All right, so now it's enabled OSPF on this interface as well as this interface. Now let's close that, get into this one here. Let's go on to router 2. Router, OSPF, process ID of 1, network, 192.168.20.0, and remember wildcard mask, area, and remember use the correct area, right? Network, and then we'll do 12.12.12.0, O.O.O.O, and remember the trick that I told you, so you're getting 255 and then subtracting the 30 from a /30 subnet, which would be 253. No, 252, excuse me. So that would give you 3. So your subnet mask would be O.O.O.3 for the wildcard mask. Same thing for a /28, it would just be 15. So 28 is 240, so 255 minus 240, 15, right? Area, and then this is 2. Oh, actually it's area 0. We're doing this one here, not this one, right? Let's fix that, do up again, and then change that to 0. All right, this is done. Now let's do this one. Router OSPF 1. This load to there. Just to get a better view of what we're actually configuring. Do network 192.168.30.0, O.O.O.O, 255, area, and then this is 3. We'll do network, and then remember, it's a /30, so we'll do O.O.O.3. 13.13.13.0, O.O.O.3, area 0. And you can also change it. For example, you can, let's say we use the next available one. So let's do, so it's 0 is the network, 3 is the broadcast, 1 and 2 are the available hosts. So let's do 4 here. You can actually change it. Let me show you. So for example, you could do this. Let's just do this. Change this to 4. So now let's say this one's configured with 5 and this one's configured with 6. It will do from 4, it'll do 5, 6, 7, right? So advertise those 3. 7 is the next available one, or the broadcast. So it'll be advertising 5 and 6. All right? That's just a cool trick about using these wildcard masks. But yeah. Now let's go into this one here. And then we'll have to do this. Let's change this back to 0. Router OSPF 1 network. And this one, everything's going to be in area 0 since all of these interfaces are in area 0, right? So let's do network. Let's do this one. Let's do this one right here. Oops, this one right here first. 1.0.0.0.3 area 0. So it should, let's actually, before we, just line console 0, exit. That was just to stop any interruptions because since we're running OSPF, we're gonna have these notifications pop up, and I don't want it to mess up our configurations. All right. Network 12.12, 12.12.0.0.0.3, area 0, network 13.13.13.0.0.0.3, free area 0. So now it's established that. And then I'll actually show you how to configure the router ID. The command is just router ID. Here we'll do this, right? And then it says here, reload or use clear IP OSPF process command for this command to take effect, right? So there's two ways. We either reload the entire router. We'll just have to save everything to the running config first, or the startup config, excuse me, or just clear the IP OSPF process. I'll show you how to clear the IP OSPF process now. So do exit or end, and then clear IP OSPF, or let me show you or show IP pro. So it's going to show you the router ID, the highest manually configured IP address, which is this interface right here, right? So this is it before we clear it. Now let's clear it. Clear IP OSPF process. And then if you click enter here, the default answer is no, so we'll type in yes. Then let's just fast forward a little. That should be enough. Show IP pro. And now as you can see, the router ID changed, right? So now let's actually test connectivity. But first, let's show you the routing table. And show IP route. So it learned a route 2. See if I can show you everything. Zoom out. Click this again. Alright, so here you can see the OSPF. O is here, which is OSPF up here. So I learned the route to the 12.12, which would be here. It should actually be advertising. Let me see this one. Because it should have the routes to these networks in the routing table. Show IP. So it has it here, 30. So it should send, if we ping, it should send it here, and then it will be able to route to these different networks. So let's actually show you. But it has a OSPF route to these networks here. Let's actually attempt to ping, and we'll do it in simulation mode just so you can see ping 2.168.20.1 simulation mode, ping. Here it's going to send it to the, let's see why I sent it back. ARP. Should go back. Right. And then this one's going to send it, I think we did it here first, right? It's going to send it there. Then it should be that's STP. That should be the ping. Oh, that's LLD ping. Let's see, it should have still gone through though. It didn't. Let's see why. Actually, let's do tracer to actually see why. It's tracer. And this command just shows you it's like each hop that it takes to get to the destination 192.168.20.1. Did I? No, it's 20.2 that I configured on all of them. That may just be why. But it should be able to ping this interface here. So it gets the 11.2. This interface here. And it should have a route to here since we checked the routing table. This one's being advertised and it just stays there. We have it here. So why is it not routing over there? For now, we'll close this. We'll attempt to. So we've confirmed it's able to make it here. But once it's here, it's not able to actually get to here. Let me see. This is all 0. Let me see. Show run Pike section OSPF. So they're all configured correctly. So that's all that. Oh, since they're all point to point, 30 is fine. How about this one? It may just be this. Maybe you configured the wrong area. Show run sec OSPF. No, the area is right. This is area 2. Point to point is that. We'll see if we're able to actually ping the, see if the area is right and they've established neighbors. Let's see, because we've seen it get to here, but once it's here, for some reason it just doesn't know where to go, even though it's directly connected. We'll see if it's just this area that's isolated, like this connection here. So we'll try to ping to area 3. Ping 2.168.30.2. What if the 20.2, 20.1, so the IP addresses are fine. Let's see, reply, destination host unreachable. So I was right, it should have IP routes to these. Show run sec OSPF. Show, oh, there's a space missing. It's configured in the correct area. So why can't I ping? Let's see if we're able to actually ping from this device to here. Actually, let's see if we're able to ping 11.2 first. Ping. So we're able to ping here. How about 12.2? And we're able to ping there. 12.1. And then this is where it just doesn't know. So what is, so it's this one that's having the issues. Oh, OSPF enter area. So why is it not advertising? Oh, because I didn't set it to, that's why. I see. Router and see. So I see what happened. So remember how OSPF is a link state, which means a full connectivity map. These don't have a map to the other ones. They just have a map of this interface here and this and the interfaces that are being advertised here. These local ones. These serial interfaces on router 6. Because it has routes to these now, it's only keeping them to itself. It hasn't given that piece of the map to these 3. So that's what's going on. So router OSPF 1 network, and then we'll just do route summarization. So just one command, and we'll do /16 area 0 the /16. So only these 2 zeros have to match, meaning that only 192.168 should be the routes containing these two 192.168 should be advertised. So these ones. So now if we go here, show IP route. It should now have those as well. This 20, and it should have 30 as well. Why does it not have 30? I mean, it's been enabled. 30 falls into the /16. Why is it not being advertised? There's something here. OSPF. It's being advertised, and it has a route there. And it's in the correct one. But these two should be able to ping. We'll see about this area 3 though. Let's see. Ping. Let's just move up. 20.2. That's tracer 2, 20.2. Alright. Ping 192. Still timing out. 0.168. 20.2. I mean, it's not. Let's see for 30. 30, even though it doesn't have a route to there. It's being advertised though, so let's see. Okay. So it does have a route there. So we've confirmed two-way communication. Right. So the thing about OSPF is you have to actually share the routes that are in the routing table. So you do show IP route. Whatever you do want to share, we'll do the conf t net or enable conf t do show, and then router OSPF1. So you'll do this first, the show IP route, and then you'll look, oh, I want to share route to X, Y, and Z. So I'll do network followed by the IP address and then the subnet mask area that you want to share it to, right? So because before we only shared these three, the connected ones. We didn't have these earlier because we were just configuring OSPF on it, or configuring OSPF on it. Excuse me. First, we only had these connected and local routes because we only had the interfaces enabled and had IP addresses, and we were advertising those. That's all we were advertising. These three were hidden, right? Like a secret treasure map that wasn't shared to area 1, 2, and 3. So we had to actually share it using the network command. And once we did that, we were able to actually have all of these routers were able to have the secret treasure map fully completed there. And we're able to confirm two-way communication amongst areas, right? So that's pretty much OSPF in a nutshell. And thank you guys for tuning in. And that's about it. Thank you. Come again.